Hello and welcome to another edition of Listen Safely. I'm Russell Porter and today I'm joined by John McKenna. John's the CEO at Seize AI, a company using drones to inspect our national power distribution network. Hello, John.
Good morning, Russell.
John, can you start by telling our listeners a little bit about what Seize AI do?
Sure thing. Let me start, I guess, with the short version and then I can expand it a little bit. We describe ourselves as a company building the operating system for autonomous flight. If I break that down a little bit, autonomy maybe is a word to talk about straight away. We're on a very long journey, I think, in aviation to the point in time when machines fly themselves. And so really that's a little bit of a strapline. The reality is we're focusing on building technology that enables remote human operators to work with one or more systems that have a degree of automation on board. And the level of automation at this point in time is quite advanced, but it's still deterministic. So we use, let's say, more decision tree than black box AI approaches, which allow us to unburden the operator. And unburdening the operator means the system can do more, but also it means the operator can stand back and use their experience to ensure that the mission being carried out is done safely and efficiently and is achieving the customer's purpose. So we're leaning heavily on advanced technologies to make it possible to do things that weren't possible before beyond visual line of sight. And I guess what makes us, I guess, slightly different to many operating in beyond visual line of sight a domain is the team's background is ex-Formula One, America's Cup, hedge funds. My colleagues have spent a long time developing novel technology and trying to get it into the real world in mission critical and safety critical environments. Richard, our VP of engineering, has won the Formula One World Championships with Lewis Hamilton. Eduardo, our CTO, twice won the America's Cup with Oracle. And our VP of software has run large software teams trading billions of pounds. So true cutting edge technology is being deployed, but really it has to be safety critical, mission critical. And so that's what drives us is how can we develop tools and techniques that enables beyond visual line of sight flights to happen, first and foremost, because it's still really quite cutting edge. But second of all, how can we enable it to happen really at large scale? And what I mean by that is, how can we enable beyond visual line of sight operations to happen, let's say, at national scale, in a way where the more we fly, the safer we get? So the model is quite different. Quite often when you see a beyond visual line of sight image, you'll see someone standing in a field under a tent, and it's, several humans involved in flying a system, let's say 10, 12 kilometers away. The problem is once you start to scale that up, you get exposure to more and more people. And humans are variable. On a good day, we're amazing. On a bad day, like today, I've got a bit of a cold, I'll be suboptimal, let's say. This human variability, when you start to scale something up, let's say to a national scale, like with National Grid, starts to introduce risk and starts to introduce variability, which can mean that the value gained from the flight, let's say the data captured, might be suboptimal. When you start supporting humans and enabling those humans to be placed in a control room with the best tools and best techniques and best support and centralized efficiency and centralized learning and centralized standard operating procedures, then in theory, the more you fly, the more, particularly with closed loop learning, where you capture an enormous amount of data from every flight, process that data and try to learn from every millisecond of flight. With that approach, you should be able to increase efficiency, safety, productivity, the more you fly. And so really, if I try to wrap up that longer summary, we're trying to build a layer, an operating system that enables entities like National Grid to fly systems at massive scale in a way that scales and gets better as it scales.
Thanks, John. There's a lot in there, so can we unpack some of that?
Yeah, of course.
You mentioned National Grid a couple of times. They're your customer, I know. So what does that look like in terms of what you're providing to National Grid?
Yeah, sure. So I'll talk about some of the other customers we dealt with along the journey, and maybe why we ended up at National Grid. Maybe, Russell, we could touch upon that later. But where we are with National Grid is the grid is one of the most critical of critical national infrastructures. Increasingly, as we electrify our world, as we decarbonize our world, we'll become reliant on the grid for our cars, for our heating, for our power. And the grid is quite old. It's 50-ish years old. And increasingly the grid is being subjected to microgeneration, much more distributed generation, much more distributed use than it was before. And we're increasing the amount of power that we're putting through the grid. So the grid is becoming increasingly central to our lives and becoming increasingly critical and vulnerable as we use it in lots of different ways. So National Grid is mindful of that and investing a lot in upgrading the grid to make it fit for purpose. Obviously, it's fit for purpose, to make it even more fit for purpose. And as they do that, the methodologies that they used before to try to understand condition of the grid are less and less useful. A good example is, we're increasingly in all of businesses trying to use machine learning algorithms to support experienced engineers to decide, let's say a maintenance schedule. But machine learning algorithms are not great when you feed them unstructured data. If you take general overview photographs and then ask it the condition of a component, it's difficult for the machine learning algorithm to figure out what is the component you're talking about and then to diagnose the component. But let's say if you were to feed an image of an insulator, one component on the grid, from exactly the same position and orientation and distance every single time, a machine learning algorithm can radically more efficiently understand the condition of that component. And if you understand the position of that component in 3D space, then every single photograph of that component can be pulled out of all of the photographs. So you can see that same component from many different angles and very quickly and efficiently understand if the component is okay or not. And so our technology enables National Grid to have their own very experienced in-house drone team to operate systems from beyond visual line of sight at national scale, to be able to capture that sort of data. The data that will help them and their partner, Keen AI, who does the machine learning analysis, to enable them to extract much more useful data from the imagery and from the 3D models that we capture during the flight. So it's effectively moving towards a grid that's self-diagnosing.
So your drones then, they're able to provide that level of precision with every single measurement and every flight that you fly?
Yeah, and we should break down how we achieve that, I think, in our business model. So when I describe us as providing an operating system, we're focused on the core technology that makes this possible. Increasingly, our operating system is being deployed on third-party platforms. So we're not a platform builder. There are great platforms out there, and you'll use a different platform for different types of jobs. In the case of the grid, our first third-party platform will be built by a company called ISS Aerospace. And so that's the platform. It's got our core tech on board, and National Grid to operate it, and then machine learning analysis done by Keen AI. So we're part of a puzzle. And then, yes, our particular part of the puzzle is to make it possible to fly commodity hardware with an experienced drone team in a way that captures highly structured, highly focused data, which is optimized for machine learning. And the really interesting thing is, machine learning algorithm is a classic for rubbish in equals rubbish out. Machine learning algorithms are fantastic, but truly if you can't feed them structured data, there's not a lot they can do. So we can radically change the efficiency of the whole chain across data capture and analysis if we can feed structured data into the machine learning algorithm.
And how is this level of precision and data, how's that being received by National Grid, by your customer?
Extremely well. They, I mentioned before, they have a lot of experience with this problem. They have been flying helicopters with an in-house team for decades on the grid. They've been flying drones and state-of-the-art drone, DJI M300 and others on the grid since 2017 with their own in-house team. They've been using machine learning algorithms with Keen AI since 2018. So this, and then in fact they've done their own beyond visual line of sight flights with GGI M300 and FPV. And so this is not a team that's trying to wrap their head around the problem for the first time. This is arguably one of the most experienced condition monitoring teams in the world for the grid. And yet still, when they first saw their system, they were blown away by it. And really, it's all about the data. So what they saw was we can deliver them very structured data in the form of 2D images. So the images are component level, position and orientation and distance relatively fixed, fixed to centimeters, including framing. And then second of all those images are geotagged in a 3D digital twin that we capture in real time. So it solves for several different things. It solves for feeding the machine learning algorithm the sort of data that the machine learning algorithm can efficiently process. But because each image is positioned in the 3D digital twin, it solves for what they call orientation. So previously, a machine learning algorithm might diagnose a problem, but the next question was, well, where is that problem? All the insulators look the same, and so they had to capture data in a very sequential way so they could look back and forth through images that were taken before and after that one to try to understand, really only using humans, where was that image. We now solve for that automatically, but as I said before, we also, by understanding the position and orientation of the camera at the time of the photograph, with every photograph, if you click on an insulator, you can automatically pull up all of the images that are taken of that particular insulator. And some of them will be deliberate, some of them will be because the insulator is in the background of another shot. And so that allows the machine learning algorithm to say, I can look at an item from many different angles to understand if it's in good condition or not. And then the next thing it enables you to do is to look at an entire circuit. So a circuit for the grid is kilometers long, and it includes many, many insulators and many, many different components and cables. But you can actually, because you understand the physical structure, the 3D digital twin, and all the images, you can say across this entire circuit, here's the condition of the circuit. And of course, maintenance happens at circuit level. You have to shut a circuit off to allow people to climb it and maintain it. So having that circuit level understanding is a total game changer for them.
Okay, so this is obviously something that your customer base are very keen on. It sounds like there's huge efficiencies in there, the novel use of new tech. What about the kind of airspace integration side of things? I know that you operate in an environment that the regulator are now referring to as the atypical air environment, and you've recently received a permission to do so from the Civil Aviation Authority. What does safe airspace integration look like for Seize AI?
So we were lucky, in fact, really early on to have met and had several conversations with a few different people, one of whom was from NATS, in fact, Jim Cranswick, who was involved in your drones business. Drones part of NATS for some time back in 2018, now at Deloitte. And early on, we met some, let's say, experienced operators in aviation and aerospace who helped us understand quickly, or at least helped us articulate to ourselves a vision for how fully pervasive operation of drones in airspace was going to play out. And the vision that we, let's say the thought process that we developed and the strategy that we've developed on the basis of those conversations, it was the, crawl, walk, run, sprint sort of approach. And for us, it was, the result of that was we set about developing technology that in theory could go a very long way, perhaps even to supporting mobility. But in the first instance, our objective was to engage with the regulator to see if we could deploy it in relatively safe environments. And so our journey towards airspace integration is by starting really in very restricted airspace and proving to ourselves, first and foremost, and then to others, including the regulator, that what we're doing is safe. And so our first beyond visual line of sight permission in April 2021 was for us, it allowed us to fly in industrial sites. So very low altitude, on closed industrial sites where general public was excluded. We were able to fly without a visual observer on site, as long as we could restrict general public and educate all those who are inside the perimeter of the site. And of course, these are people typically wearing hard hats and PPE, and they're used to dealing with far more dangerous equipment than the drone. We could operate and learn to operate safely in that type of environment. And then step by step, that was our knuckles very much dragging along the ground. Next step was, crawl. Can we get permission to fly on the grid? And when we say fly on the grid, we're flying extremely close to the grid, within meters of the grid. The benefit of that is that we're in atypical airspace, as it is now known, our infrastructure shielded airspace in the States. We're operating in airspace where it's impossible for manned aircraft to be. If they're operating meters from the grid, they've got a lot more dangerous things to think about than our small little drone. They've got 400,000 volts and a power line to think about. And so by restricting ourselves to flying in that tight confines of physical assets, we don't eliminate the airspace risk, but we reduce it. And remember, we're also reducing some airspace risk by not requiring helicopters to fly in that environment. And so we were able to have an exchange with the regulator, which, in the context of us trying to develop technology that could go a long way, seemed like a sensible next step. The other thing to bear in mind is, if you think of the team's background in Formula One, it's kind of a good analogy. Back in the 1990s, Mansell, Piquet, these kind of years, Senna, you'd push the driver out onto the track and they'd go roaring off, and you'd kind of, sit down in the pit lane and watch it on TV, and you really had nothing you could do. And then they'd come back, and you'd hope they came back a winner and alive, and it was all pretty scary days. Now, Richard's background in McLaren Formula One, they were at the cutting edge of using data and telemetry and diagnostics and analytics to try to understand system performance in real time, to be able to advise the driver and support the driver and be ready for the car when it comes in for a tire change or whatever. And now, at the really extreme end of that, these systems are exchanging about a terabyte of data with the pit wall in real time. And so the pit wall supports the driver, or supports the car, and the car supports the driver, and McLaren HQ with the team of supercomputers supports the pit wall, and FIA see a subset of data from everyone. So it's a true system of systems operating in real time with an enormous amount of data. And the closed loop enabled by that, it means that everyone's learning about system performance and efficiency, and doing that as close to real time as possible. But after a race, is able to is able to trawl through huge amounts of data to improve system performance. And so that's how we work. When the regulator allows us to fly, we capture about 1 gigabyte of data every minute we fly. And we then have that data to try to trawl through to pull out nuggets of information that allow us to improve system performance for the next time we fly. And then we have a partnership with Microsoft that allows us to do simulation. So before we ever deploy an algorithm, we can test it at large scale in simulation to test that it should be safe before we actually go out and fly.
I really like the Formula One analogy, and I have heard it a few times in relation to drone operations. And I'm keen to have a little talk with you about how bringing together Formula One, America's Cup, hedge fund management, that high performance piece comes together. But before we perhaps do that, I'm keen to understand where your pilots sit, if you call them pilots, your drone pilots. So I'm thinking here the FIA is essentially, in your analogy, the Civil Aviation Authority.
Yep.
But where's the pilot? Are they the driver? Are they on the pit wall? Or are they back in HQ?
So the pilot is the driver of the car. It's still the case, and I think will be the case for some time, where the remote human pilot, of course, in this case, they're not sitting on the drone, in our case anyway, they're sitting in HQ. And we don't think of it as our HQ, we think of it as National Grid's HQ or Cyberhawk's HQ, or, it's really, we enable third parties to operate. So the pilot sits in a control room, or indeed can sit in a van out in the field, operating the system. And like modern Formula One, they're working with a system that has a high degree of automation, but isn't optimal without their involvement. In the case of Formula One, the drivers are still, of course, the most highly paid and most skilled drivers in the world, but the car is doing an awful lot in real time to support them. And so the analogy holds true, I think, still in our case. The stage we're at now, the drone flies up to a pylon. It maps the pylon in 3D in real time. It does that, of course, for collision avoidance and dynamic path planning reasons. But it also does it so that the human operator can quickly place a template over the pylon, and the drone then flies a very complex mission around the pylon to capture something like 100 images, depending on what we're trying to do. And it does that flight without any involvement from the human. It's literally 2 or 3 clicks from takeoff to executing a mission which will be very complex around the asset, capturing hundreds of images. And we're not so far away from all of it being able to done. You click for takeoff and indicate at very high level what the system to do, and it will fly up to the pylon, map it, place the template itself, execute the mission, fly onto the next pylon, etc., etc. And so, yeah, the remote human then is able to do much more, but they're still very much in a partnership with the system, very much overseeing safety. And of course, in the real world, the grid is quite a structured asset, but even with such a structured asset, there are a lot of unknowns and a lot of variation, and the human is exceptionally well placed to deal with that level of variation in the real world. And machines are not yet. I think we've seen many instances of autonomy being talked up. Elon Musk is famous for this. There was a great example of his description of the Model 3 and how they were going to build that in a fully robotic factory. And then he rolled back and ate his words very publicly. And now the Model 3 is built with a huge amount of involvement of robots. But I think 2 or 3 jobs, welding, painting, and a few others now, I'm sure, are done by robots, but everything else is done as a combination of human and machine. And so for us, the human in a remote control room working with robotics can achieve a huge amount more than an autonomous system on its own out in the field. They're still quite one-trick ponies. And you don't add a lot of cost by having a human in charge of a system, particularly when they can drop into the system, activate it, do a job, and then close it down and move on to the next system. Their involvement massively increases the return on investment for the client, because that system can do radically more with a human involved than it could do if it was just on its own.
John, you clearly know an awful lot about this field, and there are lots of analogies that you're using around sort of Formula One, America's Cup, and you mentioned Elon Musk there. I'm pretty sure our listeners are keen to know a little bit more about your background, if I may. How did you get to be the founder and CEO of Seize AI?
It's an interesting journey. And the way I look at it now, although it's always a little bit self-fulfilling, the way I look at it now, it's a closed circle, but it didn't always feel that way. My father was a structural engineer, very passionate about structural engineering, was a fellow of Institute of Structural Engineers and president of the Institute of Structural Engineers in Ireland, and his own practice. And so I grew up drawing structures at the kitchen table with my dad. And I am, I guess, trained to be an engineer like that, but I think deep down, that's what I am. I'm an engineer. I think in very logical, structured ways, mostly. And, everything I do is in spreadsheets, including things like calendars, which shouldn't be in spreadsheets, but, it's kind of how I think. So I started off as an engineer, which was the right career path for me. There wasn't a lot of different types of engineering in Ireland at the time, and so I just did what my father did, which was structural engineering, and I really enjoyed it. I did an undergraduate degree in Dublin, got a scholarship to Imperial College in London. I did a master's in structural steel there. And then I joined Arup, which is really the preeminent structural engineering firm in the world. And I worked in a dynamic structures and lightweight structures division, which was a specialist division doing some of the more out there structures. And so I got involved in the Angel of the North, and I got involved in Lord's Cricket Ground and a few other structures, a famous structure on a earthquake zone in Turkey. And I really enjoyed that. For 6 years or so, I learned a lot. And then my learning started to plateau. And I think I realized that I missed something. I could make a building stand up, but I didn't really understand why they cost as much as they did. And I realized I didn't know much about business at all. So I did a lot of studying at night and then interviewed for strategy consulting firms And I ended up jumping into a company called Maricon Associates. Maricon Associates is one of the companies that created value-based management, or managing for long-term shareholder returns. And for me, it was a really logical way of looking at a business. So investors give companies money, and you have to manage the business to return capital to shareholders, or they won't invest in the company anymore. And so what I could see is, in the public domain, people talk about profits, but they don't talk about profits after return to shareholders, and that seems bonkers to me. A bank makes an enormous amount of money, but if it doesn't return money to shareholders, it's dead. And so profit after the cost of capital seemed a very logical way for me to look at the world, and I really enjoyed their framework, and so worked there for 4 years. I worked with Barclays and ABN AMRO and Capri Schweppes, and we'd go into businesses, rip their business apart financially and operationally, and try to understand where were the value, what parts of that business were creating value, so we're returning capital beyond the cost of shareholders. And that was really interesting, and many businesses still don't think like that. So I learned a lot about business, and for 4 years enjoyed it. But then I started to realize that I was too far from the coalface. I actually like to be in the weeds doing things. So after looking at financial services and telecoms, I joined a small group of people that were building a sports marketing company in an emerging domain of outdoor sports. And so for 10 years, we built that up to the largest business in sailing, one of the largest businesses in outdoor sports. We created marathons and road bike races and polar explorations and around the world sailing events, and I learned a lot about real business. So the theory of, the hallowed halls and the sharp suit faded pretty quickly. I was strategy consulting, and I was at the coalface photocopying, and so, we went from 5 people to 100 or so, and then I stepped out in 2011, 2012, and it was subsequently sold to a Telegram group, a company in France. And what I was trying to do at the time was return to engineering in some way. I at that point, had an understanding of engineering, had an understanding of finance and strategy. Now I really understood how businesses work, and I'd done a lot of sales, which is a very dirty word for an engineer. I'd really understood the value of sales and how to do it in a B2B context. And I wanted to get back into engineering in some way to see if I could close the loop. And so Seas is really the loop closed. In Seas, I lead the business from a business development point of view and a financing point of view. We collaborate very closely on strategy and product, the manifestation of strategy, myself and Eduardo, Richard and Damien, co-founders. But they are, of course, doing the engineering. And my engineering background allows me to understand at a high level what they're doing. But of course, I don't have the skills or the knowledge or the time to really deeply get involved in engineering. But my high level understanding of it is, I would say, relatively strong for somebody who doesn't spend a lot of time in that space. So, yeah, I think my career was circuitous, but now means I have many of the skills required really to be able to understand how to pull quite a complicated business together.
Thank you, John. And I think it's fair to say that you're leading the way in terms of what Seas do. It's clearly obvious within the drone industry. We've spoken about lots of different topics there, so thank you very much. You've touched on safety, regulation, automation, the role of the human, high-performing teams. There is one topic that's key in aviation at the moment, and it's sustainability. Probably the biggest challenge facing aviation is how do we decarbonize? How do drones play into that?
I mean, on one level, the answer is quite straightforward. There's a strong link between electrification and automation. They are not the same, but they get confused. So a lot of people see drone taxis and instantly imagine they're automated when many of them are piloted in the first instance. But there's clearly a strong connection between the two. Those two technologies are evolving at the same time, and many of the future electric platforms will have a high degree of automation on board. So they will do a huge amount to decarbonize transport and to decarbonize the world of work. when it comes to short range flight, I don't think electrification, and I'm definitely not an expert in electrification, but everything that I see, it has the power limitation, and that power limitation is going to exist for some time. And that means that it's really a short range solution. So I think in the case of replacing how workers go about their business, driving around, and small drone systems will reduce the amount of driving. When it comes to short range mobility and short range logistics, I think unmanned aerial systems will do a lot to decarbonize that work too. And then I think the longer range and much bigger problem, I think, is going to be solved with other technologies. And I really don't, SAF and other types of technologies will be addressing the longer range flights. Pulling apart. I saw a brilliant chart at Revolution Aero in Dublin a month or two ago, and it was a market sizing chart, and it showed the different bubble sizes for aviation. There's helicopters and business travel and commercial travel and private sort of travel for entertainment purposes and leisure. And it was very interesting. And each bubble was sort of bigger and bigger. And then the last bubble was this enormous bubble, just radically bigger. And it is work which can be replaced by systems that fly. I'm not sure exactly how it was articulated, but it was work which has nothing to do with aviation today, but where aviation, particularly small unmanned systems, can displace some of that work or augment the capabilities of people who are involved in that type of work. I'd say a very good example in the case of the grid is, there are about 10 different ways that the grid is inspected. But it's always interesting when you get involved in an industry that you begin to understand it's much more complicated than you originally thought. But when the condition monitoring team at National Grid want to look at their grid, they want to look at a general overview of the grid, try to understand, for example, is there a digger digging near a pylon that might undermine it, or is there some building going on too close to a power line? Or is a power line leaning over or a tree leaning over? So they want a general overview. Then they want an overview where they look at hotspots and coronas. Then they want detailed inspection of steelwork and components. Then they want to look at it from a safety point of view and see anti-climb paint and anti-climb barriers. There's lots and lots of different inspection, vegetation encroachment. A lot of that work is done with people walking the route, climbing towers and climbing trees, and a lot of that work is going to continue. But equally, a lot of that work is better done by machines, or better done with a combination of humans and machines. Much of that work is extremely dangerous when you're climbing power lines. Even if the power line is turned off, these are, falls from height, I think, is the second cause of injury and death in the UK. So reducing work from height, enabling humans to deploy their experience and their intellect and their ability to understand complex problems by being able to stand back and being supported by a robot, I think is a very valuable future where humans can do much more and be much more focused on what they're great at than just climbing. So I think that last bubble was talking about there's so much work that we do today in a way which has nothing to do with aviation, which could be augmented or indeed replaced by autonomous machines. And I think because it's not part of the existing aviation bubble, we don't talk about it very much. But that becomes part of the bubble soon enough, I think. You asked a question about integration into airspace.
Yeah.
And I think it's quite an interesting one. We have a theory. I talked a little bit about it, the kind of crawl, walk, run. That we as a business imagine ourselves operating systems truly pervasively in open airspace, but it will take some time. And for us, we constrain ourselves to flying in atypical airspace today. I think it's quite interesting looking at how this industry is addressing the problem. And there are multiple different ways of trying to fly in open airspace. It's whether it's the autonomous air taxi businesses trying to do it with pilots on board and then slowly transitioning to autonomy, or whether it's beyond visual line of sight operators in the classic sense, flying long distance but in TDAs, or whether it's us flying in atypical airspace. I think it's so interesting how we're all trying to get to the same endpoint in very different ways. And yet I think collaborating really closely, yesterday's conference, the NATS and BBLOS Forum was a very good example of it. Pulling together a group of forward-leaning people who are keen to share. So yeah, I think it's we have our way of addressing that, and it's a step along a journey. But it's just interesting. It's fascinating watching how everyone's laying out their plan to finally get there.
Yeah, and I think, you make reference there to the BVLOS Ops Forum that we ran. It was our 10th meeting, wasn't it? And I think it was sort of pivotal in that we had the CAA in the room, and we had DFT in the room, and they shared their plans for the future of flight, and they engaged you as operators, you and your peers, to shape those plans and to shape those roadmaps. And I think what it does show is A, that collaboration is absolutely key, but B, also how complex this is. And as you say, how many different use cases there are, how many variables are at play, how many means there are of taking to the skies as well. So I think the follow-up conversations after yesterday's session all kind of said, this is fantastic, but clearly there's still a way to go. But to get there is to collaborate, I think, is key.
There are so many people trying to crack this problem in so many different ways, with so many different technologies, for so many different reasons. It's very difficult to pick a common denominator and improve it, and therefore float all boats. And I think what the CAA and DFT are doing is in engaging with everyone, they're trying to understand what are those. What's the next thing I can do which has the most impact for everyone? And of course, they can't work with any one entity and move them forward because that's too focused. They're a broad-based, publicly funded entity. But I think we've all got a huge amount of empathy for the problem they're addressing and the constraints that they have. And that group in particular, I think, really responded well to having them in the room, trying not to get to, why can't you do this selfish thing for me, trying to figure out like what is the next step that floats all boats a little higher, and then being able to have that conversation with them in such an open way with them in the room, and increasingly less defensive the more they engage, and increasingly less attack the more they engage, is really powerful to do.
Yeah, it's fantastic to see that we're kind of making that progress, and we need to continue to do so.
Yeah, no, well done for you guys for making it happen. Yeah.
Well, right back at you, because it doesn't happen without the operators. So, John, thank you very much.
Thanks,
Russell. Brilliant talking to you.